Welcome back to AI Peer Review. Today, we're really digging into one of the biggest roadblocks for large language models right now: hallucinations. You know, when they just make stuff up.
Yeah, it's a huge challenge for reliability. And the paper we're looking at today argues that simply asking, did it hallucinate, yes or no? Well, that's just not enough anymore.
Right, especially for things like REG or, financial summaries, medical
Yeah.
notes. A simple flag isn't good enough. You need precision.
Exactly. We need to know where the problem is.
Which brings us to this idea of hallucination span detection, or HSD. The goal isn't just identifying an error happened, but actually pinpointing the exact unsupported bits of text.
Precisely. And that's not trivial. It's a complex reasoning task, not just simple fact-checking.
So our mission today is to unpack this framework called RL4HS. It uses reinforcement learning, RL, to try and explicitly train that reasoning capability. The big question we're asking is this kind of learned, specialized reasoning the key to finally getting accurate HSD?
Well, let's look at why they thought this was necessary.
Okay, so why do we need this specific learned reasoning? We know things like chain of thought prompting, Katie, show potential. Models can sort of show their work.
Right.
But the initial results suggested that just giving the model space to think, well, it doesn't reliably give you the precision HSD needs. Why was basic COT falling short?
So they tested this on a benchmark called RAG Truth.
Yeah.
It covers tricky tasks like summarizing, Q&A, turning data into text.
Okay.
And when they ran pre-trained models with COTI, just getting one prediction, k equals 1, let's call it the benefit, compared to models not using COTI, was, well, pretty minimal, sometimes zero.
Huh. So the reasoning steps were there, maybe, but they weren't actually leading to the right spot in the text being identified.
Exactly. The model could talk the talk, but couldn't reliably pinpoint the error span on that first try. The policy was just too noisy, maybe.
Okay, so running it once wasn't enough.
But, and this is the really interesting part, kind of the aha moment that kicked off this whole RL approach, they looked at what happened when they sampled multiple times, so increasing K.
Ah, okay. What did they find?
They found that the potential to get it right was definitely there. They use a metric, span F1, at K, which basically tracks the best score you could get if you looked at all K samples.
And that score went up significantly as K increased.
Dramatically. It showed that somewhere within the model's capabilities, the correct reasoning and the correct span identification existed.
So it's like the model knows the answer deep down, but it can't reliably surface it on the first attempt, like performance anxiety for LLMs.
That's actually a great way to put it. The potential's there, hidden in the weights, but the standard way the model generates text, its policy, isn't good at bringing it out consistently.
Okay.
And that is precisely why they turn to reinforcement learning. The goal is to take that potential, that good reasoning you see when you sample many times, and distill it directly into the model's main policy. Make K1 work reliably.
Right, because supervised fine-tuning apparently wasn't enough to capture that hidden potential. So RL it is. Which brings us to RL4HS. Now, they didn't go for standard PPO, did they? They used something called Group Relative Policy Optimization, GRPO. Why that choice?
Yeah, GRPO is quite elegant, actually. Its main advantage here is that it gets rid of the need for an explicit value function. You don't need a separate critic network estimating how good each state or action is in absolute terms.
How does it optimize without a critic, then? How does it know what's good?
Think of it like grading on a curve, maybe, or learning by comparing peers. GRPO looks at a group of generated outputs from the model.
Okay.
And it calculates the advantage of the learning signal based purely on the relative performance within that group. It basically asks which of these outputs is better compared to the others in this batch.
Ah, I see. So it's not about hitting some absolute target score, but just being better than the other attempts in that group.
Exactly. And that advantage gets normalized by the group's average performance. It makes it really suitable for tasks like HSD, where comparing one potential set of spans against another is often more meaningful than trying to guess an absolute quality score.
That sounds much simpler computationally. Less to train.
It can be, yeah.
Yeah.
It's metric-driven learning, but potentially less complex than training a separate critic.
And for HSD, the metric is key. So the reward function has to be laser-focused on getting those spans right. How did they set that up?
Well, they tied the reward directly to span F1, which makes sense. The setup was, on the surface, quite simple.
How so?
If the model correctly predicted no hallucination, meaning it output an empty list of spans, and that was correct, it got the maximum reward, a 1.
Okay, straightforward.
If it did predict spans, the reward was simply the span F1 score, measuring how well those predicted spans matched the ground truth.
Seems logical. But you mentioned this led to a problem.
It did. This setup, this asymmetry, where getting a reward of 1 is possible via a very simple output, the empty list, created a critical issue during training.
The reward hacking part. This is always where RL gets interesting, isn't it? When the model finds a loophole. What was the hack here?
Well, when they looked closely at the learning dynamics, they saw something worrying. The advantage values, the signals telling the policy what to do more of, were consistently much higher for the no hallucination predictions.
Even if the model was actually doing a decent job finding real hallucinations.
Yeah, it didn't seem to matter how good the hallucination predictions were getting in terms of F1 score. The policy was strongly learning to just prefer saying no hallucination.
But wait, if the reward is based on span F1 for hallucination cases, why would the no hallucination case always get higher advantages? Shouldn't a good F1 score get a good advantage too?
It's down to the inherent difficulty, you see. Predicting no hallucination correctly is, relatively speaking, easy. The model just has to output one specific thing, the empty list. If the ground truth is also empty, bang, reward 1, easy target.
Okay.
But correctly predicting a hallucination, that's much, much harder. You need to identify all the wrong spans, sometimes multiple ones, down to the exact words. If you miss a word or include an extra one, your span F1 score plummets.
Ah, right. So the path to maximum reward is simple and reliable for the no hallucination case, but incredibly difficult and fragile for actually finding the spans.
Precisely. The model, being a good optimizer, figured out, why bother with that super hard task where I'm likely to get a low reward when I can just predict empty spans and have a decent shot at getting the maximum reward?
So it becomes overly conservative. High precision for the no hallucination cases, maybe, but terrible recall because it avoids identifying actual hallucinations.
You got it. That's the bias.
Mm-hmm.
And to fix this, they had to introduce something called class-aware policy optimization, or KPO.
KPO. Okay, how does that work? They couldn't just scale their rewards because GRPO normalizes them, right?
Exactly. Standard reward shaping doesn't quite work the same way with GRPO's relative advantages. So KPO intervenes directly in the advantage calculation step.
How?
It specifically targets the advantage values calculated for those easy non-hallucination samples. It scales them down using a factor, alpha. They found alpha 0.5 worked well.
So it's like applying a handicap to the easy option, making it less attractive.
Kind of, yeah.
Mm-hmm.
It dampens the incentive for the model to just take the easy way out. This rebalancing was absolutely critical to get a stable trade-off between precision and recall.
That's a really important insight for anyone training RL models, isn't it? You really have to look at the effective difficulty and incentives, not just the raw reward numbers.
Definitely. Even with a smart algorithm like GRPO, the reward landscape itself can lead the model astray if there's an inherent imbalance in task difficulty.
Okay, so they developed RL4HS, used GRPO, hit the reward hacking problem, and fixed it with KPO. Let's talk results. Did this whole specialized RL approach actually pay off? How did it stack up against other methods?
The results are pretty compelling, actually. Looking at Table 1 in the paper, the RL4HS model, particularly the 14 billion parameter version, significantly outperformed models trained with just supervised fine-tuning, SFT.
Okay, better than SFT. What about against, say, big proprietary models known for general reasoning?
That's where it gets really interesting. RL4HS consistently outperformed even large, powerful models like GPT-4 and others across all the different RHA truth tasks, summarization, QA, data to text.
Wow. So a smaller, task-focused 14B model trained with this specific RL setup is beating much larger generalist models on this specific task.
Yes. It strongly suggests that general reasoning ability, while impressive, isn't sufficient for the fine-grained precision needed for HSD.
That really underscores the need for specialized training, doesn't it?
Absolutely. And Figure 5 drives this point home, too. They show that general-purpose reasoning models, even big ones like Llama 3, often struggle to get F1 scores above 40 on this span detection task. They can reason generally, but they haven't learned the specific skill of grounding that reasoning in source text to find exact inconsistent spans.
So general intelligence doesn't automatically translate to this specific verification skill.
It seems not. And perhaps the most powerful piece of evidence for this was the out-of-domain test.
Right, tell us about that.
They trained a smaller RL4HS model, I think it was a 7B model, on only 2 of the RLA truth tasks, say summarization and QA, but not data to text. Then they tested it on the held-out data-to-text task.
So it had never seen that specific type of task during its RL training.
Correct. And even that out-of-domain RL4HS model still performed significantly better than the large general-purpose LLMs on that unseen task.
That's huge. It implies that learning the process of span-level verification via RL, even on different tasks, transfers better than just relying on general reasoning abilities.
Exactly. It highlights that training with these specific span-level rewards is incredibly efficient and arguably necessary to build robust HSD capabilities. Generic reasoning is great, but it's not tailored for this kind of rigorous, grounded verification.
Okay, this is making a strong case. To make it even clearer for you listening, let's walk through that case study they included, the benchmark eatery example. It really shows the difference in the reasoning process itself.
Yeah, this is a great illustration. So the situation is an LLM generated an article about a restaurant based on some reviews.
Okay.
The generated article claimed the restaurant offers catering services. But if you look closely at the source data provided, particularly the structured list of attributes, the business itself listed catering services is not mentioned.
Ah, a subtle inconsistency. Easy for a human, maybe even a basic model, to miss if it's just reading generally. What did the standard pre-trained model do here?
The pre-trained model, using its general COTE reasoning, did a broad check. It looked at business hours, scanned reviews for keywords related to parties or events, kind of a high-level pass.
So general reasoning.
Right, but because it wasn't specifically trained or incentivized to perform that strict check against the structured data, it missed the discrepancy. It concluded incorrectly, no hallucination. It applied the wrong kind of reasoning for the job.
Okay, it failed the detailed audit. Now, what about the RL4HS model, the one trained with the span-level rewards and the CPO fix?
The RL4HS model behaved very differently. Its learned reasoning process looked much more like a systematic, almost rule-based check, the kind you'd want a detector to perform.
How so? What were the steps?
It essentially did this. Step 1. Identify the specific verifiable claim in the output catering services. Step 2. Explicitly cross-reference that claim against the most reliable source available, which was the structured attribute list. Step 3. Note the inconsistency catering services isn't in the list. Step 4. Conclude the claim is unsupported and mark the exact span, hallucination list, catering services.
It's more methodical. It didn't just reason about the text, it performed a targeted verification against the source data.
Exactly. The span-level reward forced it to learn that kind of faithful, grounded consistency check. Rather than just performing generic reasoning about the topic, it learned the right process for HSD.
It learned to audit, not just explain. Okay, pulling this all together, what are the main takeaways for listeners working with or deploying LLMs?
I think there are two really crucial points here. First, RL is a very powerful tool for HSD, but it's crucial that the reward signal is tightly aligned with the actual goal, in this case, precise span F1. When you do that, RL can take that latent reasoning potential we saw with high case sampling and bake it into a reliable policy.
So align the RL objective directly with your end goal metric.
Got it.
And the second point?
The second is about that reward imbalance. The discovery of reward hacking and the need for capo highlights a potential pitfall in many complex RL tasks. You have to be really careful about how the structure of your rewards might implicitly bias the model towards easier but less useful behaviors.
Right. The model will find the path of least resistance to reward, and you need mechanisms like capo to make sure that path actually aligns with the hard work you want it to do.
Precisely. It's a reminder to really scrutinize the incentive landscape you're creating.
Okay, that's super practical. Now, for the final thought, pushing beyond this paper, what does this capability suggest for the future?
Well, it raises a really interesting system design question, especially for RH systems. We currently treat these hallucination detectors, even sophisticated ones like RL4HS, as post hoc checkers, right? The LLM generates something, then we check it.
Yeah, that's standard.
But if these RL-trained models become so good at fine-grained, almost real-time verification tied to source data, why wait? Could we integrate this kind of learned verification during the generation process itself?
Like a continuous safety check, as the model writes.
Exactly. Could you use this learned reasoning not just to detect hallucinations after the fact, but to actively steer the generation away from making them in the first place, turning the detector into a sort of co-pilot or internal guardian during generation?
That moves from post hoc correction to proactive prevention.
It does. And figuring out how you'd integrate that kind of fine-grained learned verification into the generation loop That's a fascinating challenge. It really pushes us to think about how these verification components interact with the core generation model. That system integration, for me, is the really provocative next step to consider.
Integrating verification right into the core generation loop. Definitely something for all of us to think about. Thanks, that was a fantastic breakdown.
My pleasure. It's a fascinating work.
And thank you for joining us on AI Peer Review. We'll see you next time.